Hello, welcome to 9.3. We are going to be talking about arcs. Okay, so we have quite a bit of vocabulary in this section. There's probably about 7 vocabulary words, and then that's in addition to the theorems, but most of these vocabulary words should be somewhat review. So let's talk about a central angle. This is an angle that is in the same plane with the circle, and the vertex of the angle is the center of the circle. Like so. So angle LKM is a central angle because it is in the center. It gets confused, central angles get confused a lot with inscribed angles, and those are angles where the vertex is on the circle, okay, and the sides are chords of a circle, where before on a central angle, the sides of the angle were radii. An inscribed angle has chords. An arc measure is the same measure as the degree measure of the central angle that intercepts that arc. So if I have a central angle that measures 60 degrees, the arc measure is also 60 degrees. It only works with central angles. We'll talk about inscribed in just a minute. So here is an inscribed angle. Now, if MN was a diameter, it would still be an inscribed angle. The vertex N lies on the circle. And inscribed you can think of like if it were an inscribed triangle or an inscribed shape of some kind. This is similar. The vertex has to be on the circumference. So here is that arc measure. It's the same as the degree measure. So the arc measure of AC, the arc AC, is 60 degrees. Now that's the minor arc. Notice I could also talk about the arc AC going the other way, where it would be 300 degrees. So we're only talking about the minor arc here. So then we have the definition of minor arc. It's the arc measuring less than 180 degrees. Minor arcs are denoted with 2 letters, and then a major arc will be 3 letters. So you would need to add another point on the circle in order to have a 3-letter arc. So if I have arc ABC, it means it's more than 180 degrees. And then a semicircle, we should know, is 180 degrees exactly. So, or a half of a circle. Okay, so we have our arc addition postulate. Hopefully we've had area addition, we've had angle addition, so it makes sense that we're having an arc addition postulate. It just says if B is a point on the arc AC, then the measure of arc AB plus the measure of arc BC will equal the measure of arc AC. And then the exact same thing is true for a major arc theorem, but it's worded a little differently because you have 360 minus the minor arc AB will equal the major arc ACB. Okay, so let's go ahead and do an example. The measure of arc AB equals 50. Find the measure of the major arc ACB. So the theorem says that I take 360 minus the minor arc, which would be 50. So 360 minus 50 is 310, and that would be the measure of the major arc on that circle. Congruent arcs are arcs that are on congruent circles that have the same measure. So first off, we would have to have congruent circles, which means we'd have congruent radii, and then we would have an a central angle that would be congruent to have congruent arcs. So here we have chords of congruent circles are congruent if and only if they subtend congruent arcs. So that means the arc AC has to be congruent to the arc XZ on these two circles here. And we always start with congruent circles, so that means the radii are congruent, right? That means that if I have congruent circles, I have congruent radii. And then we have to prove that AC is congruent to XZ by this theorem. So on page 384 is the full proof, and the shortest amount of steps that they could come up with was, well, basically they broke it up into parts, but it's basically 18 steps. So you have 3 parts in order to prove this. So it's quite lengthy, and you're welcome. You don't have to prove this one on a test. So just to reiterate, if you're given the arcs, the minor arcs, then you can prove that the chords are congruent, and that's what the if and only if means. You can go both directions. So given the arc, you can prove the chords. Given the chords, you can prove the arcs. So it goes in, it's a biconditional statement. Okay, so in congruent circles, chords are congruent if and only if the corresponding central angles are congruent, which makes sense. If your arcs are then congruent because your central angles are congruent, then the chords would have to be congruent. Like so. I have central angles that are congruent, then the arcs are congruent, and if the subtending arc is congruent, then the chord is congruent. And then the if and only if part means I can go backwards. In congruent circles, minor arcs are congruent if and only if their corresponding central angles are congruent. We aren't repeating ourselves, okay? It's just different ways of saying it. So 9.10 said the chords are congruent if the central angles are congruent. This is saying the minor arcs are congruent if their corresponding central angles are congruent. So here are my central angles are congruent, then the arcs are congruent. And if the arcs are congruent, then the central angles are congruent. And your last theorem are incongruent circles. 2 minor arcs are congruent if and only if the corresponding major arcs are congruent. So now we're not even talking about central angles at all. So if the A, B, C, and X, Y, Z are congruent, those are the major arcs, then my minor arcs are congruent. Since it's an if and only if, it works the other way as well. If AC and XZ are congruent, then the major arcs are congruent. So for your WISC summary, I have 7, I believe, practice problems. A couple of them are multiple choice. The ones that are not, you need to show me your work, and I will see you in class. Please submit these via email. I shouldn't have to say that any longer, but just as a reminder, and I'll see you in class.